Hey there, welcome back to Short Takes 331. Today we're going to talk about the adjoint operator. In a previous video, we talked about adjoints of matrices. And so with matrices, which are simply linear operators in a finite dimensional space, we talked about the dagger. So if our matrix is M, we talked about M dagger as given by this formula. So M dagger ij, so the matrix elements of M dagger are simply the transpose complex conjugate. So MJI complex conjugate. Now, more generally, to properly define the adjoint, we need to use an inner product. And so let me remind you what an inner product was. So we have a whole video on the inner product. If you haven't seen it, you can go back and check it out. But I'll give you the quick version here. So an inner product is a binary operation. It takes on two vectors and maps those onto a scalar. And these vectors could be any vectors in your vector space. And whatever formula you decide to use for the inner product will give you some scalar at the end. Now it cannot be any formula. It has to satisfy these properties. So first of all, it has to have this conjugate property that when you flip the order of the entries, you get the complex conjugate. So V with W, the inner product of V with W is the complex conjugate of W with V. Another property is linearity. And this happens in a very special way. If you multiply the first entry by a number, then that number can come out of the inner product. So xv with w is the same as x outside the inner product of v with w. And this is true for any scalar. Now, if we put x in the second entry, then by virtue of the previous property, then the x will come out complex conjugated. Why the first entry and not the second entry on this second property? We could have chosen to define it that way. And in fact, some of the time we'll do that. For our purposes today, really it doesn't matter if you use the first one or the second one, and as long as you're consistent throughout your calculations, of course. We also have, as part of our linearity property, that's the inner product of a sum, u plus v, for example, with w, with the third vector w is going to be equal to the sum of the inner products done individually, u with w and v with w separately, and then you add them up and you get the same result. So that property has to be satisfied. Finally, we have positive definiteness. And this simply says that the inner product of a vector with itself is greater or equal to 0, and it can only be 0 if the vector in question is actually just a 0 vector, so the neutral element under the sum of vectors. So again, the inner product of v with v is greater or equal to 0, and if it happens to be 0, then you have to have that in that case your vector is the 0 vector in your space. So with all that in hand, we defined the adjoint of an operator, which we will call M dagger, by this equation. So the inner product of a given vector v with M dagger applied to w is defined by M, that operator M that we started with applied to v, inner product with w. So again, M dagger on w inner product with v is the same as M with v inner product with w. And the claim, which I'm not going to prove, is that if this is true for any vectors v and w, then that completely defines your operator M dagger. Of course, we're defining this entirely on the action of M, and so it's directly connected. So M dagger and M are of course connected. And in a finite dimensional space, then that happens in the conventional way, like we described at the very beginning of this video. So if your inner product v with w is the usual sum over the components of the vectors, such that we have vk complex conjugated and multiplied by wk, then let's see what happens. So if we calculate the right hand side here, m multiplied by v, then you have mij multiplied by vj, the whole thing complex conjugated because it's complex conjugated here, and then that contracted with wi. So we have mij, vj complex conjugated, wi, and sum over ij. So that's our right hand side. And on the left, we simply have the action of M dagger on w and then contracted with vj star. And so if these two things are going to be equal for arbitrary v and w, the only way that can happen is if mij complex conjugated is mji dagger, which we can rewrite simply down here as M dagger ij, the matrix elements of the dagger, are simply those of M, but transposed and complex conjugated. And that's of course the same equation that we started with at the beginning of the video. Now it's simply showing that it comes from this definition. Now, in the cases involving differential operators in infinite dimensional spaces, where these operators can be unbound, so they can have eigenvalues that go all the way to infinity, then we have to be more careful. And I'm going to give you an example here. I'm going to leave the more formal details for a future video or for somebody else to do. There's certainly a lot of information out there. I will give you some practical information here though. So if we have the inner product of f with a function f with an operator d, a differential operator, let's say it's the first derivative, and then acting on g, then we want to find a way to put this d on the other side of the equation. So dg, we wanted to turn that into g in order to somehow get this definition. So what we're doing then is we're trying to put this operator on the other side, so that to get, like we did here, from m to connect to m dagger, we have to somehow move this m, or the action of m on v, we have to somehow move it onto w. And the way to do that, in cases where you have an inner product defined by an integral like this, is to use integration by parts. So suppose then that we're in a space where our functions are such that they decay at infinity fast enough that this integral converges, everything is nice and regular, and so when we integrate by parts, we can throw away all the surface terms, the terms that evaluate the product of the functions and their derivatives at plus or minus infinity. And so if you do that, then this derivative simply acts now on f star. And of course, we have to pay this minus sign from our integration by parts. But what we obtain as a result of this operation is that now we've gotten the operator to apply on f, to be applied on f. So we move the operator from the second component to the first component, and that's really what we're after when we're trying to find the adjoint. Now here, it turns out that it looks like the adjoint is just minus d, and so the d dagger is simply minus the derivative, which is not d itself. So there's a minus sign of difference, and so we cannot say, for example, that this operator is self-adjoint. And this, if you know some quantum mechanics, this may be a little bit surprising, because we know that this first derivative operator in quantum mechanics is the momentum operator. But it's not just that. Actually, for the momentum operator in quantum mechanics, we have an I. And so if you account for the I here, and you account for the complex conjugation property that appears in the inner product, then you will get that P is the same as P dagger, which makes sense because the momentum should have real eigenvalues, because it's in principle something we can measure. And so we would expect that to be a Hermitian operator with real eigenvalues. And this is how you work with differential operators, like the first derivative or second derivative. It's often the case that you use integration by parts to connect an operator with its adjoint. Now, formally, I should say the definition of the adjoint in infinite dimensional spaces has to be handled with some care. Especially if you're trying to define something like a self-adjoint operator or a Hermitian operator, which are two things that may not necessarily be the same when you're working in an infinite dimensional space, and you have to worry about limits and operators whose spectra go to infinity and so on. So I'm leaving all those details out. I just want to get you some practical information. So our adjoint operator defined like we did, defined in this way with the inner product, will inherit its properties, or will get all its properties from the inner product, from the three properties of the inner product that we saw before. Now, of course, the adjoint operator will inherit linearity. It's still a linear operator, but we also have other interesting properties, such as this one, that a dagger dagger is the same as a, and we'll prove this below. It's also true that the dagger inverse is the inverse of the dagger, and the sum of the daggers, or rather, the dagger of the sum is the sum of the daggers. And then finally, the adjoint of the product is the product of the adjoint, but in reverse order. And if this sounds like what happens with the inverse or what happens with the transpose, that's exactly right. And in fact, in the case of matrices, the dagger is simply the transpose complex conjugate. And well, that just simply says that we have to flip the order like this because of the transpose. The complex conjugation will not flip any order of anything, but the transpose will. And so you see where it comes from with that definition. But you can prove this also using the inner product. And so now I will show you how to prove the first one with the inner product, but you should try to prove this one as well using the inner product. So our starting point to prove this identity is the inner product of a given vector v, any vector, with a dagger dagger applied to w. And so by definition of the adjoint, then this object is the stuff that we're calculating the dagger of, and so we can put that on the other side of the inner product by definition of the adjoint. And now we have this dagger acting on this first component. Now we would like that to be on the second component, or at least that's what I would like to do. And so we can do that by taking the complex conjugate. So I flip the order and use the property of the inner product and pay the complex conjugate here. And so this, then we have this equality. And now the dagger is here on the right, but then if that's true, then this is the dagger of A, and I get to put A on the first entry of the inner product. I still have the complex conjugate along for the right, and finally now I can affect this complex conjugation and flip the order once again, and so I get V multiplied by AW. And so this chain of identities then tells me that this A dagger dagger must be equal to A, because this is true for any vectors. We didn't use any property here of the vectors at all, as long as this all these inner products are defined and we're safe. And so if that's true, then it must be that A dagger dagger is equal to A. And that's it. That's how you prove this property. And in the same way, you can prove, for example, this other property here or any of the other properties of the inner product. And that's it. That's all I have for you today. If you enjoyed this video, please like and subscribe. And if you're looking for a tutor in physics or math, you can contact me at shorttakes331@gmail.com, or you can leave a message in the comment section below. And I will see you next time.